When it comes to alkenes, we also need to talk about another type of carbon, and these are the allylic carbons. So A-L-L-Y-L-I-C. Allylic carbons are the carbons that are adjacent to the carbon-carbon double bond. So in this structure, we actually have three. 1, 2, 3. And these three positions sit in a unique area of the molecule because they are available to the double bond in terms of a resonance structure. And if we were to look at an alkene, typically if we're going to do reactions that are specific to sp3 or tetrahedral carbons, these are actually going to react before the others. So even if I were to draw out more chains here, these are probably the three carbons most likely to react, specifically if we do something that creates an ion or we do something that creates a radical. So let's say we introduce something like Br2 plus light, and we're going to create a radical. The radical is actually going to be more stable on these positions than it is at any other position in the carbon chain, and there's a reason for this. It's resonance. So let's say we put the radical here. What can happen is that we can resonate, and we can put the double bond there. And because we have this resonance structure, we've stabilized the radical versus if we put it here. While a tertiary radical is more stable than a secondary radical, it's not going to be nearly as stable as a secondary radical formed here or here because it doesn't have the resonance stability. We can put a radical here and it's going to be more stabilized. Now, it's not going to be as stable as these two positions because these are secondary and this is primary. But again, if we were to throw a radical up here, we could definitely do some resonance to create stability here. Now, this is also going to add complications to your synthetic scheme as well. And the reason I say it's going to add complications is that because we do get this resonance structure, now we can have, we put a radical here, a reaction here, or a reaction here. So this is something to keep in mind with allylic hydrogens. If you have a reaction that creates an ion or a radical on one of these allylic carbons, there is a possibility to get resonance, which is what's stabilizing those positions, which means that your product may not necessarily, your reactant may not necessarily add to the carbon you're looking at. But good thing to take away from this video is that this is why allylic hydrogens are much more reactive. They are nearby the double bond, and because of resonance, any type of ions or radicals formed will be stabilized.